Hello physics students. In the last video, we learned that the force of gravity isn't just between objects and planet Earth or any other planet. We learned that it's universal. In other words, if you take any two objects like these tennis balls, they're attracted to each other. And that attraction you could calculate from the force formula that we learned in the last video. However, we also learned that that attraction between two objects that are small, like these two tennis balls, is tiny, minuscule. So small you can't even notice it. If I put these on a flat surface like this together, it's not like they stick together like magnets, because that force is so tiny it's hardly noticeable. What you need is for one of the objects or both to be enormous, like planet Earth. Now, if planet Earth and this tennis ball attract each other, you can see that effect of that force when it falls. So we learned about that yesterday. But still, even with planet Earth being so big, so massive, pulling this, the entire Earth is pulling this ball down. And set against that is me. And look, I can win against the entire planet Earth, me, if the Earth is pulling with force of gravity. So gravity is, once again, weak, even when one of the objects is very large. But if you think about it, we just kind of accepted that two things attract each other. But we never talked about what causes that attraction. Okay, the masses do, but think about it. There's nothing between these two objects, like no string, no nothing, no arm of one thing pulling another. They just interact through space itself. And that becomes even more fantastic, more amazing when you think about maybe not two tennis balls, but the Earth and the Moon, hundreds of thousands of miles apart. And there's literally nothing between, a vacuum. And yet they're attracted to each other. Why? Or take even more extreme, the Earth and the Sun, which are over 90 million miles apart, nothing but vacuum, emptiness, literally nothing between them, and still they attract. So what causes that attraction? Well, interestingly, even Isaac Newton didn't know when he thought of his force of gravity. I'm not going to read you the front cover quote, but if you read about it, if you read it yourself, he calls it an absurdity that one thing should attract another thing through nothing but a vacuum, with nothing in between. That's an absurdity to him. So what does Isaac Newton say causes that attraction? He says, gravity must be caused by an agent, be material or immaterial. I have left to the consideration of my readers. Either it's a physical object causing it, or an immaterial, like what, a ghost? I don't know. He leaves that up to you to figure out. So he comes up with this theory, this law of gravitation, and he says, I don't know what causes it. It's absurd that it happens. You figure it out. Okay? So today we're going to try and answer that question with today's topic, the gravitational field. So this is one possible answer, the gravitational field. If you have a body like planet Earth or any mass, what it does is it does something to the space, some kind of warping of space. That warping is what we call a gravitational field. This is a graphical representation of that field. It's a vector. And it points toward the planet. And notice that at a particular radius, all these arrows are the same length, but they're just pointed inward. If you go further out, the arrows get smaller, which means the field is weaker. But notice this arrow and this arrow, at the same radius out, the field is all the same size. Go further out, the field gets even weaker. So this is a picture representation of this thing called gravitational field. Here's the formula for how you can actually calculate its magnitude. Okay, G, that constant on the front cover of the reference table, the mass of the planet, how far you are from the center of the planet, squared. And then that thing, that mysterious field, causes force by the mass that's in the field times the field creating force of gravity. So it's just another step in the thinking. We used to say mass 1, mass 2 attract each other with a force. Now what we say, the more accurate description of that interaction is mass 1 creates a gravitational field pointing toward it. Mass 2, when it finds itself in that field, feels a force as a result of that field equal to mg. Now, this formula is not on the reference table directly. It is indirectly. That's what this is saying. Let me show you a close-up view of the reference table. So here's the back cover. Okay. Here's the original force of gravity formula we learned in the last video. Here's this formula which we learned earlier in the year. Notice the little g function you can get by dividing one of the masses out of this formula, which just leaves you, if you divide one of the masses away, gm1 over r squared. The formula I wrote on the board there. So this formula combined with this formula, dividing one of the masses away, gives us the gravitational field formula around a planet. Okay, so that's the answer that Newton didn't know, is that there's a field created causing this force. Okay? Let's take a look at an example. First example. Determine the gravitational field at the Earth's surface. Now you may notice that this little g value looks the same. We've already used little g. And we'll see why in this example. Plug in gm over r squared. Now where do we get g? Front cover of the reference table. But where do we get the mass of the Earth and the radius of the Earth? I mentioned this in the last video. That data is on the front cover as well. So here we have capital G right at the top, 6.6 on 10 to the minus 11, and you need all those units. And then if you scroll down, here's the mass of the Earth, as I mentioned already in the last video. And then the radius of the Earth right here also. So we're going to take those values, plug them in, here and here, here, and we get 9.83. You might be thinking, 9.8, that's the number we had earlier in the year. It is, okay? So this is a redundant calculation. We really don't need it because we already knew G was 9.8. By the way, if you look it up on the reference table, it's 9.81. Why is it 9.83 here? Because of the spin of the Earth on its axis. More information than we need to know, but that's the value. The advantage of this formula, though, is that we could find the G on the moon, for example, plugging in the mass of the moon, radius of the moon, Jupiter, Mercury, whatever. We could plug in and find G in other locations without even going there. Okay, so it's more universal than just remembering G is 9.8 here. It's some other value at a different planet. Here we could calculate it. Okay, now another kind of example which I won't solve is basically pointing out that there are three variables in this formula. G, which is 9.8 on Earth, but it could be something else somewhere else. The mass of the planet, the radius of the planet. So another example, out of the three variables in the formula, two of the three are given and you solve for the third. The hardest one is if you're asked to solve for the radius, because then you have to remember to cross multiply first, then divide and take the square root. So there'll be an example like that in the homework. All right, so let me create a pause to allow you to catch up with the notes if you need it. Okay, so let's look at some other things here. The patterns that we could see in this formula. For example, how does the mass of the planet affect the gravitational field of the planet? Again, when you're asked to graph relationships, I said this many times, never guess. Look up the formula on the reference table, and the formula will tell you the pattern. So we looked this up, we figured out from these two formulas there. We jot that down. Now we see that m is in the numerator, n to the first power. It's not squared. If it were m squared, we'd have a parabola like this. M to the 1 power, hey, we know how to graph y equals x like this. And there it is, the answer. How about if we plotted the gravitational field versus the radius of the planet, keeping the mass constant. We look up the formula, we see r is in the denominator, r squared. That makes like a y equals 1 over x graph is like this, like we saw in Newton's laws. Well, y equals 1 over x squared looks very similar. You could try it on your calculator and plot it in the first quadrant only. You'll see a descending curve like this. So there's the pattern, gravitational field. The other thing I want to mention is remind you what altitude means. Okay, so altitude is how far above the surface of the planet you are. And then we have to, these problems kind of show up commonly. So let's suppose we know G on the surface of the Earth is 9.8. And I say, what is the gravitational field strength at an altitude equal to 6.37 times 10 to the 6th meters? And you kind of have to recognize, and if you're not sure, you say, that number sounds familiar. You have to at least know that it's familiar. And if you look up on the front cover of the reference table, as I showed you before, you can verify that that's the radius of the Earth. So we say we're at an altitude of 6.67 times 10 to the 6th meters. 6.37. That's the radius of the Earth. That's our altitude. So if we move from here to here, we could see that the radius above the surface of the planet has effectively doubled. Okay? So altitude of the radius, r has doubled, and we could look back in our formula and see that when you double the radius, because of the squared, you're making the denominator 4 times as big. In other words, you have 9.8 divided by 4 at that altitude. If we have the altitude of the diameter of the Earth, so here's the diameter of the Earth. If we rise above the surface of the Earth that far, what we've done is we've taken the radius, which is, let's see, maybe I'll use green, from here to here, the radius, and now we've effectively tripled the radius, right? 1, 2, 3 times the original radius. In other words, we have 1 divided by 3 squared, 1/9 of 9.8 up there, okay? So let me create a pause and allow you to catch up with these notes if you need to. All right, so that's the gravitational field. 2 objects don't directly pull on each other. One creates a field, and then this one responds to the field by these 2 formulas, okay? Now, I've mentioned this multiple times, and I'll mention it again because I like it so much. Then there's the third part, Albert Einstein, who said that there's another way to look at the attraction between this ball and the Earth, and that's that the Earth warps space and time. And that, how the time and space are warped, is what accounts for this motion, or even this projectile motion of an object going like this. And so that's even more fascinating, more deep, really kind of blow your mind stuff. A lot of fun, but again, not part of the curriculum. You just need to know how to calculate gravitational field and the force caused by that gravitational field. All right, I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next physics video.